This part of the lecture is a just in case you need it type of lecture. If you're studying for the CSP and you find instead of using the multiplier tables as we did in the undergrad, instead of using the equations to find the multiplier values, there's an alternative method that is quicker and dirtier, and so it might be easier to do on an exam, and so sometimes they'll show you this method instead. For this part, finding the NLE multipliers instead of using the equations, we're going to use figures on page 177 to 178 of your Kodak book. For the first three multipliers, we're going to use this figure on page 177. This will give you three of the multipliers. Then we'll have another set of figures to find a frequency and asymmetry multiplier, one each, and then you'll still need a table for the coupling. But using this figure, this graph, you can find HM, VM, and DM on this graph. You want to use the legend that HM is the solid line, so this will be your HM right here. Okay, so your solid line. Our example problem that we just worked, the employee picking the toad off the J-hook conveyor, our H was equal to 23 inches at the origin, so 23 inches. And so our distance in inches is down on the x-axis, distance in inches. We want to find that 23 inches. We can see that we've got 20, 40, so this would be 30, this would be 25 right here, and so 23 is probably pretty close to right here, so 23 inches. We want to extend that up until it meets the HM line, so that solid line. So it meets it about there. We want to then extend the line over to the y-axis to find our multiplier value. Wherever that crosses this horizontal line right here, wherever it crosses, that'll be our multiplier value. And here we could see it's approximately, if this is 0.4, this is 0.5, 0.6, it's probably about a 0.43. So approximately a 0.43. So whatever your H is, from 0 up to 24-ish inches, you want to mark it on the x-axis, extend the line vertically until it crosses the HM line. Wherever it crosses, you extend that horizontally over to the multiplier axis and then identify what your multiplier, your HM multiplier is. Okay, the other two operate similarly for V. For V, we can see that it is the long dash line. So the long dash line, so it starts here, goes up over, and then down. In this case, in our problem, the employee was reaching 70 inches vertically to get to the tote on the J-hook, so 70 inches. Our 70 inches happens to be right here. So 70 inches is our limit. As we saw, people can't lift or small females cannot reach higher than 70 inches, and so that is our limit. And so we would follow this up until we see that the VM ends. We would take that over to our y-axis, and I haven't drawn this very straight very well, but you can see that it crosses at approximately 0.70. So VM would be 0.70. And then lastly, our D will be our last curve where it's a fully dashed line. If our D is 40 inches, we would mark it here as DM or as D. We would follow this up until it hits the dashed line. Again, extend it horizontally over to the axis and identify that oops, I see I'm off a little bit, but our DM is approximately equal to 0.86. Okay, I've drawn a little bit less than that, but it should be about a 0.86. Okay, so that'll be your 3 multipliers, and you can see that once you get a little bit of practice, you can do this very, very quickly. Okay, so that takes care of HMVMDM. To get to FM is just a little bit more complicated because you have 3 durations, and so we were at a 3 lists per minute for 2.5 hour duration. You can see that our solid line is 1 to 2 hours. Our small dash is 2 to 8 versus our long dash was less than an hour. We're at 2.5 is the dash line here. And so I'm going to follow this up at 3 lists per minute, 3 lists per minute frequency, 3 lists per minute, follow this up, and then find, oops, where it crosses would be somewhere here. Somewhere here. I didn't draw it very well. It looks like it's about a 5.51 or so. 0.51, 0.52. And then lastly, our A is equal to 0. There was 0 degrees of twisting, and so we followed it up to see where it crosses. It crosses at 1.0, and so our AM is equal to 1.0. And then lastly, our coupling, we're stuck with the table. Our coupling, we were right there. So we still use the table for the coupling. Okay, so that's kind of a quick and dirty way to find, rather than using all the equations, just use the figures to find your multiplier values. The last thing I want to mention in relation to the NIOSH lifting equation is, what if you have test variables that are changing with each lift? For example, if you're stacking or unstacking a pallet, or if you have, well, this pallet task here, but you also have to lift something over here, or you're unstacking these back here, you have different tasks. Your options are to, 1, perform a worst case scenario. And in that scenario, you're looking for what is the hardest part of the task. If the hardest part of the task is okay, then the entire task should be okay. And so on the unstacking the pallet, you would probably think that, well, this bottom sack that is furthest away from the worker, that is the lowest he has to reach, that would probably be the worst case. And so this would be the one that you evaluate rather than trying to evaluate all of them. So that's one approach to the problem. Okay, so go with a worst case. It's either the highest, the lowest, or the furthest away. A second way is to perform a multitask analysis, so multitask and NIOSH lifting equation analysis. This you want to use a piece of software such as ErgoWeb to do. You're going to evaluate for example, each layer. Each layer you would still have the same, you'd have to consider the loading, the H and V at the origin, H and V at destination, the distance moved, asymmetry, frequency, duration, coupling. And so that might be layer 2, layer 3, layer 4. You would have to measure all those variables for that layer, so for that particular task. Okay. But again, it's very tedious. You want to use some software to do this.